we just
Okay, here we go. We're going to pick up right where we left off. So, I believe this class had gone through 11, is that correct? Okay. So just a reminder, look here. Okay, remember, I haven't given you a homework assignment yet, but the concepts you're learning, you do need to get those memorized. The stuff that is on the sheet. So we're at the point where we've got the blue is a graph of the position of a moving particle. The red is a graph of the velocity of the moving particle. This big long statement here says that the average velocity is the same thing as finding the change in position divided by the change in time. Oh, please.
So I have my calculator in my car. Is it like worth it to go grab it?
Which kind do you normally use, Drew?
TI-83.
Just borrow mine for now. It will work.
Okay.
Thank you. It does help to be able to follow along.
Very glad and I'm pretty good.
Video? Okay. Got it. Really works and as the batteries are dead. Okay. So look, memorize this. If you're looking at the position graph, at this point, time equals 0, position equals 0. Over here, time is 1, position is -3. If you draw a straight line from one point to the other, you calculate the slope of that secant line, that's the average velocity, the slope of that line. That's what this equation says. Make sure as you memorize these concepts, you're very specific. Don't take a shortcut and say, oh, average velocity means secant line. No. Average velocity means secant slope of the position graph. So you've got to have the complete thing memorized. Question? Awesome. Okay, next page. Okay, we want to change the window from 0 to 7. So same formulas but new window.
Is the X max that we're changing?
Right, so I hit window, leave my X min at 0, change my X max to 7, zoom fit again. Questions? Okay, cool. Okay, the sheet I gave you last time that had the two graphs on it, I'll borrow Ashley's for a minute. Okay, this is what you're looking at now. This graph is this graph. This has the acceleration depicted as well, so there's a third plot. We'll add that in a little bit. But I gave you the big picture just because it does help to be able to see a large version of the little screen. Then you use your calculator to kind of do some precise computation. Questions? Awesome. Okay. Back to here. It says, new thing to memorize. Velocity is defined as the instantaneous rate of change of position. So the symbol here is different than the symbol here. This one was average velocity. The new one is instantaneous velocity. Make sure you recognize the difference. I probably won't say instantaneous velocity very often. When I say velocity, I imply instantaneous velocity. The AP test does the same. They say find the velocity at time 3 seconds. They mean the instantaneous, like what is the velocity precisely at exactly 3 seconds. So, please, Dan.
Just look at the slope of that line.
So yes, that's the big idea. that one way to find the instantaneous velocity is to look at the position graph. So you got to make sure you're looking at the right graph. Find the instantaneous slope of the position graph at the time you're interested in. So that's what this symbol means. Velocity is the instantaneous rate of change of position. So notice the difference. This says dx over dt. Reminder to everybody, calculus demands precision far more than any previous class you've ever had. Like, every little detail is important. If it's not, I'll let you know. Hey, this is just kind of a good to know thing. So dx is not d times x. The two symbols go together. It means an infinitesimal difference in the x values. And x represents position. So, look here. When we found average velocity, we had delta x. Delta means change in x, but it's the change in x between two separated points. Like the one I showed you where from here to here, the value of x drops by 3, like the difference in x. Instantaneous really actually means the same thing, and I'll show you in a second. But the difference is infinitesimal. So the two position values are so infinitesimally close to each other that there's no space between them. That's not really possible, but that's the general idea. Infinitesimally close. So d means infinitesimal difference in x. Delta means some sort of actual, easy to see, finite difference in x. So very similar symbols, but slightly different meaning. Questions? Awesome. So that should look similar to you. Finding the average velocity, take the slope between these 2 points. Finding the instantaneous velocity, take the slope between these two really close points. Okay. Another symbol you must memorize. dx dt means exactly the same thing as x prime. So the x with an apostrophe, we say prime. I don't know where that comes from, but that's how it's said. And it means, as Danny said, the tangent slope of the position graph. Average velocity was the secant slope of the position graph. Questions? Superb. At t equals 6 seconds, the tangent slope of the position graph is what? So what that's saying is, come over here to 6 seconds and identify at that moment in time the slope of the position graph. So you would be looking for this secant slope. That secant slope's value will be the instantaneous velocity at that same moment in time. Question? Okay, we don't really know how to calculate that right now, so I'm going to show you what was done, like how it's actually calculated. So look at this picture. This is the same graph. I'm going to move some points here. So let's move this point up and this point down. So notice point A is sitting at time equals 6. So that's the same point I drew on the other picture. So here's time A. We'd like to find the tangent slope at that point. Well, what Newton discovered was the following. He said, okay, I can calculate the slope between point A and point C easily. I just plug in numbers, I find the points, I do y2 minus y1, x2 minus x1, I can find the slope. And I've got the computer doing that for me because the details are a bit tedious. So there's the slope of that secant line. So Newton knew how to do that. That was not new information. And he realized that if this is a graph of position, the slope of that secant line would be the average velocity of the particle between these two times. But he wanted to know what was the velocity of the particle right at time 6, like at that instant. And his thought was the following. Well, what if I make the secant shorter and shorter and shorter? So the average velocity, like the time between the points here, becomes shorter and shorter and shorter. His theory was, well, if I get close enough to A, I should get a pretty good estimate of what the velocity is exactly at A. So that's the computation he did. So I've got the computer doing it for me. So notice how as I move these points closer, you no longer can see that they're separate lines. Like they're becoming what we would think of as the tangent line. However, the two slopes are still different. Here they are. You can compare them. Because we're still not close enough to make them exactly the same. But Newton's idea was that if you really could get infinitesimally close, you would be able to determine what the slope in the middle must be. It must be like sandwiched right between them. And that's a place where he ended up using the idea of a limit. Because you can't calculate the slope with one point. You get undefined. So he said, I can't find that slope, but I can find the slope between 2 points that are really, 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 really close. If I go to the limiting case where they're so infinitesimally close you can't even tell that there's any space between them, that should be the tangent slope. And he literally did limit to the right, limit to the left. So here's my secant to the right. Oops, wrong button. So here's the secant to the right. Here's the secant to the left. Then you bring them in close. You do need to memorize that that's how tangent slope is computed. Do secant to the right, secant to the left, bring them in close. That's how you find the tangent slope. I won't really ask you much detail beyond that. Just, hey, remember that's how we find a tangent slope is by doing two secants. And that's partly why we studied limits. So. I was curious if I could get this computer software to zoom in so close that the two secant slopes would actually look like the exact same value or extremely similar. And then I got a little bit, I told you all that I'm like the dog and up, I distract easily. Yeah, I spent 40 minutes trying to get close. After 40 minutes, I had to wake myself up and say, wait a minute, this is a waste of time. Stop trying to get close. But here's the zoomed in version if you're curious. So the grid disappeared because I got so zoomed. It was hard to zoom in on this software. That's why it took 40 minutes. So here's the two slopes. I can't touch the dots or the thing crashes. That also took some time to keep refixing everything. And I finally figured out, okay, now don't do this, do this. And, you know, it's very exciting. Look. Can you see that the two slopes are almost identical? When the two secants become so close to that center dot, you really do zero in on the actual tangent slope. Okay. Now, my point is not exactly where it needs to be. It's like at 6.005 or something. So when we do a computation in a minute, it's not going to come out exactly like this, but pretty close. Question? Awesome. Back to here. So we're looking for this tangent slope. Let me show you how to do that on the calculator. So grab your calculator. Okay, we want the tangent slope of the blue when time is equal to 6. Warning. If you have a TI-83, the method I'm about to show you can give you an answer for which you will lose points on the AP test. But the 83 is not accurate enough to use this method on the AP test. All the other calculators, as far as I know, are just fine. If you have an 83, be cautious. So I'm going to show you two methods. The method I show you now will cause an error on the 83. It won't be accurate enough to get full credit on some problems. So you go second calculate. And it's right here, number 6. I want to find the derivative, the tangent slope of a curve. So type 6. Got to make sure you're on the right graph. I am. I'm on the blue. I want to say where to find the derivative, so I type in the time. 6, press enter. The calculator reports the tangent slope. So this is the y-coordinate, negative 78. The tangent slope at time equals 6 on the position graph is 155. Very close to what I showed you on that other graph. So, question? The calculator is actually doing, one second, sorry. The calculator is actually doing what I said a minute ago. Tangent to the left, sorry, secant to the right, secant to the left. Get them in really, really close. It calculates the slope. That's all it does. Okay.
Can you show that?
Yeah. So you're right here on the graph screen. You say second in the calculate function right here. And the one we want to use is derivative. Derivative is the name of this little expression. So derivative means tangent slope. So 6. And make sure you're on the green graph. Choose the time you want. The calculator tells you. Anybody else? So anyone in this room have an Inspire? I can't remember. No Inspire. Oh, you have Inspire. Did you get it to work?
Cat?
Did you get it to work? Did you get this to work?
No, it's strange.
Try to see if you can get it to work. So. Question? Okay. Oh, please.
I was just wondering, my X and Y didn't pull up on my calculator.
Oh,
Is that
yeah, the color has kind of an
Okay, I'm just checking. Okay,
I'm
but-
pretty sure, right? Like on yours didn't either. You don't get the XY? Yeah, just the
Okay.
derivative. No worries. Please.
So she got 155 like with like 0, 0, 0, 2, and then I got 156. So
Let me
like,
look. Hold on a second.
yeah.
The 155 with lots of zeros is fine. It's just, I've got mine just set to round off sooner. So that's not a huge deal. This is more important. That's interesting. So, which one's yours? Yes, you forgot the ring steps. So you're grabbing this thing slightly different. That's why it's your graph. Anybody else? Cool. So back to here. So the tangent slope of the position graph is 155.
I have a question.
Yeah, please.
Will we be able to use our calculators to calculate that on the test or whatever? Like, will we be able to just...
Gotcha. So on the section of the test where calculator is allowed, they will have questions where they expect you to know how to calculate that tangent slope using your calculator. So that does come up. It's not a heavily tested item, but they do expect you to know how to do that. We will, in the few weeks down the road, we'll learn how to calculate it without a calculator. Just not yet. Like today I showed you the theoretical way to do it by finding a secant slope to the right and a secant slope to the left and then finding the limit. They don't actually test you on that method, so I don't spend a lot of time practicing it. But it is important that you be able to understand the general idea. They will test that concept. Does that answer your question?
Yeah.
Perfect. 2 points. Anybody else? Sweet. Go back here. Okay. I want to just see if how many of you can make the connection. I don't know if it's a hard connection or an easy one. Hard and easy is kind of relative. So look at this formula. We just found the tangent slope right here to be 155. You get it to work, Daisy? Okay, 155. There's another way to find this tangent slope on this particular graph, at least on the calculator this way. There's another way I can find this tangent slope. Look at this equation and raise your hand if you can see what I'm talking about. Like another way to use my calculator, find the slope right here. You wouldn't see another way to do that other than what I just showed. It's really, 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 really simple once you see it. It's a connection that you need to understand and memorize. So I'm making you think about it for a second. Anyone see looking for him? Another way to find that this tangent slope value is 155. All blank books. Maya.
Would you go to the other line and find x because that's the velocity? Or no?
Right idea, the wording was just a bit off. That's exactly the right idea. Look here, 2 points for Maya. It says that the tangent slope of the position graph is exactly the same thing as the instantaneous velocity. Well, right here we have a plot in red of the instantaneous velocity. So I can go to time equals 6 on the red graph and simply find out. So right there, the x-coordinate is 6. That's the time. But the y-coordinate will be the velocity at that time. And this velocity must be exactly the same as this tangent slope. That's what this equation is telling you. Okay? Maya figured it out, but the rest of you must memorize that. And it must make sense. You have, like, okay, there's a set of concepts that I would say these are the most important, and there's kind of second, third. This one's over here is the most important. Like, there is no more important concept than understanding that when I look at the tangent slope on the blue graph, I'm looking at the y-coordinate on the red graph. They mean the exact same thing. And they'll test you to see if you understand that connection. Question? Awesome. You can go here and do it real quick. Just hit trace. Make sure you're on the red graph. Type in time equals 6, and sure enough, that y-coordinate is 155. Now the calculator isn't making the connection. The calculator doesn't know that it's velocity and position. So the calculator actually does calculate this slope by going secant to the right, secant to the left, shorten them up, and then it just finds the y-coordinate there. So, questions? Cool, next thing. So the velocity is also 155. So just to make sure you can do, I got to show you one other thing. Okay, I showed you how to find the derivative on this picture. One problem with that is you don't always get the correct rounding that you need for the AP test. So let me show you how to do it from the main screen. So go back to the main screen, second quit. Type math 8. On yours, Boston, do you have the graph? Do you have this graph graphed on your calculator? Yeah. So do you know how to get that graph? Have you ever graphed on the Inspire?
I have graphed, but no.
Not recently.
Not recently.
Come up here for today. Come sit right here. Anyone else in the room have an Inspire? Cool. Did you buy it or rent it, Boston?
I bought it.
Okay, just making sure. So rented, we've switched you back to the easier ones. So just sit here, calculator out. Oh, you're all set up. So type in this one. Press enter and do it F2 and type that. From the main screen on the 84, type math 8. Look on the math menu. 8 says numeric derivative. So choose 8. Okay, you see the same symbol that we saw here. Look. Okay. We want to find the change in the position divided by the change in time. Again, don't memorize the symbols, memorize what the symbols mean. So this is change in position divided by change in time. So on the calculator, the denominator here needs to be the time variable. Let's check the whole room. Let's So raise your hand if you know, on our calculator, what symbol are we using to represent time? Just raise your hand. You got to keep track of this. I got to get you more engaged. What symbol on the calculator are we currently using to represent time? If you don't know, talk to someone who does until you do know. Like, you've got to keep track of the meaning of the symbols. If you're losing track of the meaning, you're slipping back into the really bad habit of trying to memorize what I do, and that won't work. What symbol on the calculator means time? Talk to somebody who has their hand raised. What symbol on the calculator means time? I want to see what his hand does. What symbol on the calculator means time? Show me your hand. Show me your hand. What symbol on the calculator is representing time? Sarai? How many knew it was X? Show me your hand. Point, two for Sarai. So right here, hey, we need to find how the position is changing with respect to time. We need a dt on the bottom. But on our calculator, X is representing time. Like I said a moment ago, okay, when you take the first test and get your score back, you'll figure out whether or not you memorized my steps or you understood and memorized my concepts. And you'll know by your score. If you slip into memorizing steps, you're in trouble. So you've got to keep track. X is time on the calculator. We want to find how the position is changing. Raise your hand if you know what symbol represents the position on my calculator. It's on all the 84s have the same symbol. The Inspire is different. So what symbol on the 84, 83 is representing the position? We want to find the change in position with respect to time. So what symbol is used to represent the position? Talk to somebody who has their hand up. Come on, get everybody's hand raised. What symbol on the 84 are we using to represent the position? On my piece of paper, the symbol is X for position. But on the calculator, it's a different symbol. What symbol is it? Show me your hands. Come on. More hands. More hands. 1 second. Drew.
Why?
It is Y, but we have to be specific. It's the Y1 symbol. Because no worries, because we've got something in Y1 and something in Y2. So on the calculator, we need a Y1. How many knew it? Point and 2 for Drew. So you do the alpha, choose Y1. Just a second. Awesome. So we're going to find the change in position with respect to time. We want to do it for a time value of 6. 155. You need me to do that again? Hey.
Why do you put Y1 in there?
So what I'm looking for is the velocity at time 6, which is equivalent to the derivative, that's what this symbol means, or tangent slope of the position. So on the calculator, this X here is really Y1. My position formula is in Y1.
Oh.
Did that make sense? Is that your question? 2 points. Please, Rachel.
I get why it's Y1, but I can't find it on the calculator.
Oh, I'll help you with that in a second. So look up here. I'll do it again. So you got the math 8 okay.
Mm-hmm.
And the X okay.
Mm-hmm.
To get the Y1, do alpha and then F4.
Okay.
You see that?
Oh, yeah.
No worries. You got the list?
Yeah.
Okay. 2 points for Rachel for asking. You know, not get it to work, just wave at me. Yes? Well, you have an 83, right?
Yeah.
So on the 83, it's still math 8.
Yeah.
I need to change my mode here just a second so I can demonstrate for you. So the 83 works great, but this is where it just becomes a little tougher to use. So you go math 8, and you get that symbol, correct? I still need to say Y1. So I use the vars key for variables. Go to Y variables. Choose function. Y1. Good to there? Okay. Then you have to type comma. I'm not sure, but I think it's X. If I'm wrong, I'll fix it in a minute. Then comma again, and then 6. Close parenthesis, enter. Yeah, that works. Anybody else? Let me check Boston's real quick. Okay, so your equations are right, but we got to get the window. So you have to hit menu. You want to go 0 to 7. Zoom fit. Now you got to do the zoom fit. So back to the menu. There we go. Wow. Derivative. We're going to do it from a, you get another tab over there.
Yes. Is there like an accent?
Yeah, the whole time.
Oh, I don't want to do equation. I want to calculate, but I want to do tab. Same document. I want a new document.
You're so cool. I'm fluent Latinese. Say it. In Latin. What's everybody does?
Switch back to 1.1. So what I did, there you go. So from this screen now, I'm going to pull up this menu right here.
Today?
So you do the same thing I did. You use X, that's your time. Now this one's different. So you do variables. You grab F1 as your position.
I'm so good at chemistry.
Move over.
Actually, yeah.
The bar. Pull that one. This is the bar. Say X equals. That makes sense.
Do you hate them?
No, they're okay.
I'm sorry.
Okay. If you have an 84, but it's operating like this, I can fix that. I'm not at lunch. Some lunches I have meetings. Sometimes I just have to lock my door and get some work done. But some days I'm here. It's like today I'll be here at lunch. If you come by at lunch, it takes like 5 minutes. I just hook up your calculator and upgrade it, and then it will work just like the 84. So.
Wait for an 83.
No. So if you have an 84 that is functioning like an 83, it can be upgraded. If you have an 83, the only way to upgrade it is to grab your wallet. Sorry. You can. I did hear that they still have a lot of color 84s for rental. If you're interested in paying the $20, it's up to you. The 83 will do everything you need. It is just a bit more cumbersome to get things typed in. So, Weston.
I just have a problem with my calculator.
Let me come back. Hold on.
So I know that this is supposed to be called like 5 on the box.
What?
When I try
What? She's like, I hate all these men. I liked it though. Could have been a lot worse. Because sometimes that you sit right behind him, and then every once in a while you'll say one thing and you're like, that's how happens.
That's crazy, and I'm like,
He says that he hates the
I don't agree with this. I just know what I'm saying.
She's like, I'm just there. Yeah, you're just trying to. Did you say Abby? Did you say Abby? I'm so close to you. I'm like this. I'm like sideways. Well, it's like, you know how you're like listening to something like this? I don't know why I was doing it with this hand, and then I don't know why I was like sideways. I was like, what is that?
Oh my gosh, my entire family is watching Sword Art.
Whoa, that's so fancy. Yeah.
Look up. Make sure this connection makes sense to you. Look here. Okay, make sure you can do it this way as well. That's the way I'll do it on a test, because I don't want to take a chance of getting an error on my graph. It's just not as accurate. So I always use the main screen. Back here, I kind of misexplained something. It caused some confusion. Okay, the idea is that the tangent slope of the blue graph will match the y-coordinate of the red graph. We can find the y-coordinate on the red graph by going here, hitting trace, make sure I'm on the red graph, then hit 6. So I don't want the slope at this point, I just want the y-coordinate. So notice there's no dy dx or anything, it's just the y-coordinate.
Okay.
Anybody else? Yes, please.
So why do we even have to know how to find the slope if we can just find the y-coordinate on the
Oh,
other
gotcha. 2 reasons I can think of. There's more, I'm sure, but they will expect you to understand the connection. So in some cases, they won't give you the velocity graph. Like you'll only have the position. And so you'll have to know that, oh, I find the tangent slope on the position, that's the same as the velocity. So they expect you to know the connection. The other thing that you must know is this, everybody. Raise your hand if you know, like, if all you have is the position, like if all I have is the position graph, I can create the velocity graph. Raise your hand if you know how I would do that. One person. So all I have is the blue. I don't have the red at all. I can use the blue to create the entire red graph. How do I do that? You need to know how this works. If you're not seeing it, pay close attention to make sure it makes sense. If all I have is the blue graph, how do I find the red graph? I've got a few people. More hands. There we go. If all I have is the blue, how do I find the red? you'd like to get some points, talk to somebody who has their hand raised. All I have is the blue. How do I find the red?
Because this chapter is the same as the y graph.
Hands up, who knows? Mine's like, this does not sound like a fun task, but I do think I understand the idea. Hey, hands up, who knows? Ellie?
Do you have to find like the tangent slope of each of different points and then sort of graph it out?
No, perfect. So you literally would go along the blue. Hey, yeah, and I'm not going to have you do it because I'm not a big fan of busy work. But you literally find the tangent slope everywhere on the blue, and every tangent slope on the blue becomes a y coordinate on the red. Memorize that, make sense of it. Super crucial. Every y coordinate on the red is simply the tangent slope on the blue. How many knew it? Show me. 2 points. Okay. Question. You need to memorize that. Now, in a few weeks, we'll learn some techniques that make it go like immensely faster. Okay? Like we learn how to come up with a formula for the tangent slope of the blue. Once you have that formula, basically that's the formula for the velocities. Okay, next thing. Go find these two real quick. Write them down. Stop me if you need help. So answer the next two, please. Right here, number 14.
The most random. Isn't that cool?
Right, that's the one.
Imagine though, it's like this thick. Or feet or hands never grew. And baby feet. And little guys. Just little guys.
Yeah.
So
what I'm doing here is for that velocity type X prime means the slope of the I want to.
Is that a human part? No, just like a hot dog with
The little ball.
Yeah.
You should have both of these. Who has this? Come on, hand, show me. Who has both of these calculated? So what'd you get, Tristan?
-49.
For both?
Yeah.
Hands up if you got that. Show me. 2 points. Okay. Remember, look, I hate busy work, so this is not meant to be busy work, but I am trying to make sure you understand that X prime means the slope of the position graph when time is equal to 4. So it is important that you keep reminding yourself that I can find the slope of the position graph by saying math 8. Let's see, position graph is y1. And if I find that at time equal 4, that's the value of the position graph slope at time equal 4. But it's also the same thing as the velocity at time equal 4. So remember, from the main screen, you can do this as well. Alpha, choose y2, that's my velocity, and calculate the velocity at time 4, and they'll be exactly the same. So, questions? Awesome. Okay, cool. Back to here. Did you get that to work on yours? Yeah. Okay. So this is negative 49. And also negative 49. And I'll get rid of that for now. Okay, it says at what time does the particle stop moving left and start moving right? How do you find this time using the position graph? How do you find this time using the velocity graph? So I want everyone to raise their hand who can tell me, looking at the position graph. I just want an estimate. You don't need to use your calculator at this moment. Just want an estimate. Raise your hand if you can tell me, when does the particle stop moving to the left? So at what time approximately will the particle stop moving to the left? Here's the situation. Particle starts at the origin and it moves left. At what time does the particle stop moving left? And how can you find that on the position graph? Going back to Kess's question, you've got to know how to do it from both graphs because you don't know what they're going to give you. And they'll expect you to understand both graphs. So how do you look at the blue and know when the particle stops moving to the left? Hands, please. Come on. How many know? Talk to somebody with their hand raised. Figure it out. Come on.
New word comes across this. It's appears when you five seconds to one of those. Oh, yeah. Just position in there on Tessa's right. And wait, but isn't this one the velocity one? No. No, the bottom one's the velocity. What's Y1? The top or the bottom? That's Y1. The red one's Y2? That's why I asked you why is it Y1? Because I was confused because I thought the red was Y1.
Show me your hands. When does the particle stop moving to the left? Let's go Chase.
Slope's positive.
Slope of what?
The velocity.
So when you say, all I'm asking is this, hey, got to make sure you're precise. So the slope of which graph?
I don't know. Blue.
I don't know, sir. 2 points for a good shot. So how do you know when the particle stops moving to the left? Hands, come on, show me. I know when the particle stops moving to the left. Let's go, Jane.
It passes the 0 on the X.
So you're looking at the blue or the red?
The red one.
The red one. So we want to know how to find out. So what I'm trying to prep you for is an AP question. You're doing just fine, 2 points. AP question where they don't give you the red at all. All they give you is the blue. So how do you know from the blue graph that the particle has stopped moving to the left? Hands, come on. How do you know from the blue graph, Noah?
It's like when the slope is 0 and starts to turn back to be positive, right?
So Noah's looking at this. Right here, the slope of the blue graph is definitely 0. The tangent slope of the blue is 0. Nod if you can see that. Okay, so the tangent slope right here is 0. When the tangent slope of the blue is 0, that means the velocity is 0. That means the particle has stopped. So the particle, let me trace for you. Make sure this clicks. Don't let me move on if you're not seeing it. Here's graph. If I go trace, go back to 0, I'm going to follow the blue. Look at the y coordinate. The y coordinate of the blue tells you the position of the particle. So notice how the position is becoming increasingly negative. That means as time goes forward, the particle is moving to the left because the position is becoming more and more negative. That's what you're focused on, is that position value becoming more and more negative. Question? Right down here at the bottom, about in there somewhere, the particle actually stops, but only for an instant. Then it begins moving to the right, and you can see that because the values of the position are becoming less and less negative. Now we know the particle is moving back to the right. That needs to make sense to you. If it doesn't, just wave and I'll do it again differently. Waving? Okay, cool. Oh, hey, sorry.
So will that happen like all the time when the slope of the position graph is 0? Like the line of the velocity graph will always be like crossing?
Gotcha. Hey, 5 points for Hayden. Seriously. That connection is really, really big. Whenever the tangent slope of the position graph is 0, the y-coordinate on the velocity graph has to be 0. Because every y-coordinate on the velocity graph is a tangent slope on the corresponding position graph. It's perfect. So that's the other way you can tell that the particle has stopped moving to the left. Because notice here, if you follow the red, all these red dots have a negative y-coordinate. Negative velocity means the particle is going left. Right here, the particle stops going left. It actually stops. The velocity becomes positive. The particle starts moving back to the right. Those 2 points are perfectly aligned. The spot on the blue graph where the tangent slope would be 0 and that spot are perfectly aligned. Now, one warning. The position graph can do this. It can come down, flatten out, have a slope of 0, meaning the particle stops, but then it can keep going down. Okay, so the particle actually does not move back to the right. It just goes left, stops, and then keeps going left. And then the velocity graph would do this. It would have negative values, meaning the particle is going left. It would have one value of 0, meaning the particle stopped for an instant. Then the y values would keep going negative again. They would never become positive. So the particle would never move to the right. Questions? Superb. All right. I want to make sure you can do that on your calculator. So go back here. Apologies if you already know how to do this, but I found about half don't. You can find this little bottom, like where the particle stops moving to the left and goes back to the right. Choose second and the calculate menu. We want to find the minimum, the bottom of the blue graph. So you have to make sure you're on the right graph. Then the calculator is asking for the left bound. That means move the cursor to the left of the bottom, the left of the minimum. So I arrow back this way. Stop right there. It doesn't have to be perfect, just somewhere to the left. Press enter. Now move it to the right of that spot. It's asking for the right bound. Press enter. It wants you to guess, so you just move it kind of near the middle. Close enough. So that time is 4.848. That's when the particle stops going to the left and starts going back to the right. Please.
I think instead of like moving the arrow along the line, you can just enter like an X value, and then it'll put that as like.
Oh, well done. No, it's perfect. Thank you, Isaac. So what Isaac, let me see if I can demo what you're talking about. So he's correct. If you can look and see that, hey, I'm at 1, 2, 3, 4, near 5, you can do this. Minimum. You can say, oh, left bound 4 is close. It'll draw the left bound at 4. 6 is far enough to the right to surround it. 5 is a good guess. Is that what you're saying?
Yeah, it just only works sometimes though, because like if you don't know what the range is.
Yes, very good. Well stated. But it is quicker if you kind of know the window. It's very good. Points for Isaac. Anybody else? Okay, the other way to find that point is to do what Hayden said. It's to find this point. They're in exactly the same place. You must understand that and memorize it. So on the red graph, do second calculate. Choose 0. You want to find the 0 of the red graph. So I got to get on the right graph here. So now I'm on the correct one. Left bound again. Enter. Right bound. Yes. Should be exactly the same value. So I'm not having any trouble with that. Is anyone getting like 1.6 times e to the minus 11 here? Okay. What that means is the guy who wrote the routine for the calculation of the 0, he couldn't get it to work any better. So he did the best he could, but he can't get it to say 0. So what it's saying on yours is like 0.00011 times and then 1/6. So you just have to look at that and say, yeah, that's as good as it's going to get. So. 2 for Trey. Anybody else? Superb. Go back here. Now remember, we don't have homework tonight again because it's just taking a little while to make sure these concepts make sense. But you must memorize the ideas. So whatever you need to write down, to make sure you won't forget that there are 2 different ways to figure out when the particle stops going left and starts going right again. Make sure you write that down and get it memorized. Question? Take a moment and write that down while I check on, did you get yours to work? Do those? Flat so you can see it. So it's probably 6. There you go. Choose minimum. Sure, now you gotta somehow choose the graph. So you gotta move the cursor and select the right one. Not the red one, the blue one. There we go. There's lower bound looks good. Let's wait for you to find it. Very good. Perfect. And then you can find the 0 as well. Analyze your graph. Do the menu thing again. You would need help with anything on the calculator. Okay? No. So we're finding the minimum of the blue. It's a low spot. But the minimum of the blue corresponds to the velocity change, which is negative to positive. So we're finding the 0 on the velocity graph. No, plugging in 0 means you want time. So we don't want the time to be 0. We want to figure out right. We want to figure out what time is the velocity. Why is it? Good job. Allison and Maya, calculate. Just make sure.
Thanks.